Hello, my name is Carly Taylor, and today I will be presenting to you flexible batteries. So, again, my name is Carly Taylor, and I'm a fourth year student here at the University of Florida, where I'm majoring in mechanical engineering and minoring in zoology. Growing up, I spent a lot of time outside with my dad doing repairs and maintenance on trucks, tractors, machinery, so I really fell in love with putting things together and working with my hands and finding solutions to mechanical problems. I grew up in a small rural town in Florida, so I never personally knew of any engineers, and college finally exposed me to that career option. In my time at UF, I've traveled abroad studying biodiversity in the Bahamas and out west, and I spent quite a bit of time doing genetic research on marine invertebrates through the Museum of Natural History. And now I am a TA for Design and Manufacturing Lab on campus. I started interning with Duke Energy doing power distribution engineering, and I have another rotation coming up this summer, and I plan to start with the company following my graduation in December. I've always had broad interest in energy and utilities infrastructure, which has, of course, been increased by my involvement with Duke Energy, and I've also been very interested in sustainable energy options. So, batteries are certainly a topic of interest for me. And on these pictures in the center is me working for Duke. I really enjoy fishing. Toward the bottom left is another job that I had with the Museum of Natural History with the Lepidopteran Center. And toward the right is one of my biodiversity studies. So here on the left is a list of some different designs for flexible battery electrodes. And then on the right is sort of a diagram of the different things that will be desirable as we continue to develop battery options. So flexibility is on there. Certainly it's important to have, the portability, the bendability, the ability to conform to different objects, to be stretchable, to be thin, for uses in many, many applications. So technology is constantly evolving, and we are seeing the development of flexible and wearable electronics, which really encourages the commercialization of flexible batteries. Typically, portable power sources are bulky and rigid, perhaps heavy, so they cannot be properly integrated into rising technologies like smart textiles. Beyond wearable technology like Apple Watches, there may be medical applications such as implants, epidermal sensors, or artificial skins. Flexible options are, in fact, urgently needed to keep up with future technologies. Toward the right, again, we've got flexibility, but also the ability to be integrated into the various technologies that are rising, and then also multifunctionality. So essentially, saving costs, saving volume, saving weight, making sure that things are as efficient and responsive as possible. And another part of the integration is design aesthetics for anything such as, Apple Watches. It has to be able to be aesthetic as well. Toward the left is some of the different options. Thin film and island bridge will be the two that we most focus on during my talk today. The thin film battery is not pictured here on this slide because it's not quite as pretty to put into a diagram, but it is by far the most straightforward option. So that structure will include a variety of layers that involve the packing, current collectors, electrodes, and electrolyte. As we know from mechanics of materials, when a layered structure is bent, the outer surface will undergo tensile strain while the inner surface experiences compressive strain. The middle layer will experience minimum strain, and that's an important property to consider when composing the layers of a flexible lithium-ion battery. The packing material or encapsulation most utilized in designs thus far is PDMS, thanks to its chemical inertness, and cross-linked polymer structure, which allows for greater flexibility. The thin film structure, unfortunately, does not provide great capacity opportunities, and the structure is difficult to scale up. By comparison, the island bridge structure, as pictured on the left, involves decoupling the current collectors and the electrodes to address the capacity problem. It involves sandwiching the electrodes and the electrolyte and connecting them in islands and connecting all those islands with flexible current collectors, which can allow for energy storage components to make up about 80 to 90% of the total volume of the cells. So rather than making the cells themselves super flexible, they might stay a bit rigid, but they're connected by a flexible material. Stretchable batteries provide even more obstacles than simply bendable batteries, since active materials of batteries are currently not intrinsically stretchable. The island bridge structure does allow for some stretchability, as the flexible connection structure connects the rigid islands. Thus, the active materials do not have to bear the stress or strain of stretching. Stretchable electrodes can be designed with a wavy structure to make them more stretchable. A combination of a cathode, anode, and PDMS fluid on pre-stretched PDMS substrate was produced in research and could go through 30% strain for 2,000 cycles. Another produced example in research could go through 400% strain for 1,000 cycles of stretch strain. However, it is important to note that 2,000 cycles or 1,000 cycles of stretch strain does not come close to the amount of cycling that a consistently worn device might endure in the period of a day. So this is rather primitive technology that is being produced by research as of 2020, 2021. To the right here, we see another example of a model for a flexible battery in more fabric form. So here you can see that the cathodes and anodes are interwoven using and protected by a gel electrolyte and then layered on either side. So that woven design is what would give them a more flexible geometry. So these are two examples. And we will also talk about the use of nanostructures. So since traditional electrodes can be brittle and prone to failure during repetitive deformation, nanostructured materials are also an option since they can help address these various issues because they offer improved strength, flexibility, and resilience, as well as potential for enhanced ion transport. However, the nanomaterials encourage greater surface area and thus have potential for greater contact with the electrolyte, which can have adverse effects like increased rates of side reactions. The packability of the material may also not be as good, which results in poor volumetric energy density, and nanostructures can be very costly. So here in the figure, we've got nanofibers, nanosheets, and 3D nano architectures such as porous foams. So some of the properties, applications, and examples. More than anything, it's important to note what application you're using said material for and making sure that you choose the correct nanostructure, whether it be 1D, 2D, or 3D for your application, especially since they can be so costly, and also to minimize bulk and maximize performance. Finally, we'll talk about some of the various applications a bit more in depth. I'm talking about implantable batteries, drug delivery systems, biofluid activated batteries, biodegradable batteries. So in addition to just creating the flexible battery in general, there are also it's important to consider other technologies such as making those batteries biodegradable. Since they are so thin and transportable, making them actually dissolve would be another great use, a great technology to develop. Biofluid activated batteries would be another instance, and where on top of the actual design of the flexible battery, there would be greater technology and research put into the battery's uses, its performance. Toward the bottom right, you have an example of water desalination. So it's also a really great opportunity to use flexible cells for water desalination cells or for solar cells. The key challenges, however, with flexible batteries are that there's a lack of intrinsically flexible active materials available to us currently, and also a lack of fabrication methods that are scalable and reliable. Also, with lithium, there are issues with stability and safety, especially as we change its geometry like we would need to so much with flexible batteries. Currently, flexible batteries are certainly in an early stage of development, especially flexible batteries with high capacities, which is going to be necessary for a lot of the rising technology. That means it's going to be imperative that researchers come up with creative designs using flexible electrodes and differing cell configurations to design effective flexible batteries. So this is just a small taste, and I will make sure to include the various papers that I used as resources and the papers in which these figures came from in my comments in the video. So thank you for listening.